In this video, we are going to start talking about the reactivity of amines. And in the beginning of this, we are going to start talking about how to prepare amines. Understand that the following slides are going to be a review because these reactions have been explained in previous chapters. So, how do we prepare amines? As you can see, amines can be prepared from alkyl halides. Now, in the following reaction, you can see that a primary amine can be made from an alkyl halide in a two-step process. Overall, you will see that there are 3 steps total. So the two-step process means that in the first part of the reaction, we can have an SN2 reaction in which sodium cyanide is going to introduce a cyano group to our alkyl halide. In the second process is going to be the reduction of that cyanide into an amine. Understand that this reaction is important if in the synthesis process what you're trying to do is extend the carbon skeleton by 1 carbon atom, because understand that in this reaction the cyano group is bringing into the starting material an extra carbon atom. There are ways that we can do the transformation to an amine, but it doesn't necessarily need to introduce one more carbon atom. One of the ways in which this can happen is that we can convert a carboxylic acid into an amine. As you can see, in this set of reactions, there are 4 different steps that have to be followed. And as you can see, the carboxylic acid first is converted into an acid chloride by converting it via reaction with SOCl2. Then, in the presence of excess ammonia, we can create an amide. Once the amide is created, as you can see, it can undergo a reduction with lithium aluminum hydride, followed by a water, aka an acetic workup, and that's how we make the amine. Now, in this strategy, as you can see, the carbon skeleton is unchanged. So it's very important that in the synthesis process, you are very careful counting your carbons to see if we are going to increase the number or is it going to remain the same. Now, aromatic derivatives of amines, in other words, aniline, can be prepared from benzene. As you can see, when we have this conversion happening, the benzene molecule first has to be nitrated. In this nitration, as you can see, the reagents are HNO3 and H2SO4, and we are incorporating a nitro group to the benzene ring. Once the nitro group has been incorporated onto the benzene ring, then there's 2 ways in which you can get to the aniline. In the first one, you have hydrogenation conditions, which is that you use molecular hydrogen and platinum, or the other way in which you can do it is by using one of these transition metals, iron, zinc, tin 2 chloride in the presence of acid, followed by a base, and that can produce the aniline. In the previous video, we have already seen that amines can act as bases, but understand that amines can also act as good nucleophiles and readily undergo SN2 substitution with an alkyl halide. As you can see in the following reaction in this slide, ammonia can react with this methyl halide, in which now we are going to be creating an ammonium salt. Then in the second step of the reaction, as you can see, the amine, in this case ammonia, is going to deprotonate that ammonium salt, and that's how the primary amine is generated. Understand that in this process, it can also be utilized to make quaternary ammonium salts, as we are going to see in the following slide. One of the difficulties with the reaction that was shown in the previous slide is that monoalkylation is difficult because the nitrogen becomes a better nucleophile as it picks up alkyl groups. So as you can see, the product of the reaction that we illustrated in the previous slide, that primary amine, can continue to be alkylated all the way to make that quaternary ammonium salt, which means now that our nitrogen atom is surrounded by 4 alkyl groups. Amines can also be prepared via substitution, via the acid synthesis. As you can see here, in this reaction, we are going to have our alkyl halide, which you can see X can be any of the halogens. We are going to react it with NaN3. That is going to undergo a substitution reaction, specifically SN2, and we're going to be introducing an N3 to the molecule. Now, once you have that A side group incorporated into the molecule, then there's 2 ways in which you can make the amine. One can be hydrogenation conditions. The second way in which you can convert it into amine is by using lithium aluminum hydride followed by water. Now, this is a better way to make a primary amine than trying to monoalkylate ammonia. Because remember that the monoalkylation, as we explained previously, is really hard because once you alkylate ammonia in the previous reaction, it will continue to get alkylated. In this way, is going to be a much better strategy to accomplish the product that is desired. Let's go over the mechanism of sodium azide reacting with alkyl halides. As you can see here, we have an azide ion that is going to be functioning as a nucleophile and attack the alkyl halide, expelling the halogen as a leaving group from our alkyl halide. Then, once that SN2 reaction has occurred, this specifically is just illustrating the lithium aluminum hydride. It is going to be transferring a hydride ion to the alkyl azide. Once that happens, understand that nitrogen gas is created in this reaction, in which the lone pair from the rightmost nitrogen is going to come and form a triple bond. The next nitrogen bond breaks. That's how nitrogen gas is produced. Then understand that the amide ion is produced, and in the second step of the reaction, that amide ion gets protonated and it results in the formation of the amine. Amines can also be synthesized through Gabriel synthesis. In Gabriel synthesis, understand that primary and secondary amines are going to be made from phthalimide, and this I think I pronounced it correctly. I think it's phthalimide. Forgive me for this pronunciation. I thought it was phthalimide or phthalimide. Anyways, the molecule that you see here, that phthalimide, I think that's correct, is going to be first creating an anion with potassium hydroxide. As you can see here, now our nitrogen is negatively charged. Once that occurs, understand that the ion that was created, it can now undergo an SN2 reaction with specifically the alkyl halide, and the nitrogen is going to be alkylated. Then, in the last step of the reaction, understand that what occurs is that we are now going to react our alkylated intermediate with aqueous hydronium or hydrazine. So we have some acid in the system, and that's what is going to be creating the amine. Understand that when we have aqueous acid, what we're going to create is a hydronium, not hydronium, ammonium ion. And when we have hydrazine, it creates specifically the amine. Another way in which amines can be prepared is through reductive amination. In a reductive amination, we can start with an aldehyde or a ketone that is first converted to an imine. After the formation of the imine, then under hydrogenation conditions, we can have that nitrogen atom receive protons, also the carbon that is double bonded to the nitrogen, and that's how we form the amine. Understand that if a reducing reagent is present, the imine can be reduced in the vial in situ to form the amine. Okay, reductive amination, as you can see in the next bullet point, can be accomplished through a variety of reducing reagents. Now, understand that sodium cyanoborohydride, which is similar to NaBH4, is commonly used because it is selective for imines. So in this slide, you have a comparison between sodium borohydride, which is the molecule that it is on the left, and sodium cyanoborohydride, which is the molecule on the right. Understand that since sodium cyanoborohydride does not react with aldehydes or ketones, it can be used in situ. So what that means is that you will add it all into the vial, and this is going to be yielding the desired amine all in the same vial of the reaction. So you don't have to do several steps. It all can be added into the same vessel. Through reductive amination, you can yield primary, secondary, and tertiary amines. As you can see from the reactions that are summarized here, let's say that, for example, we start with a particular ketone. As you can see, the distinction between primary, secondary, and tertiary amine depends on the nitrogen atom that is going to be forming that imine. So if you use ammonia, you can form a primary amine, which is what we see in the first row of reactions. If you use a primary amine, that is going to yield a secondary amine. And lastly, if you have a secondary amine in this reaction, you can yield a tertiary amine.